Good afternoon, and it's great to see everybody here again. Jack Moehle speaking on behalf of Farzad Naeem and myself, who put this talk together. This is a talk about lessons or observations from the performance-based design peer reviews. And in some ways this is intended to be kind of a fun talk. But if you see your building up here, you might not think it's so much fun. Anyway, everybody's worst nightmare in this process is that you run into this. It's a big crowd of unfriendly, unhappy-looking people who just want to make your life miserable. And that's not usually how it is. Usually it's 3 people. They come into a room, and you probably know some of them, and they have smiles on their faces. And if they're doing their job right, the first thing they say is, we're here to help you do this job efficiently and well. And it turns into a really great experience, not this experience. Okay? But I want to tell you some of the things about how the peer reviews typically are set up, how they typically operate. There are some deviations from one place to another. And then we'll tell stories for as long as time permits. All right, so peer review has a simple purpose. It's to provide an independent, objective, technical review of any aspects that relate to seismic performance. Okay, so those words are all important up there. And it's critically important to have the peer review because the building officials generally don't have the knowledge, the experience, the particular detailed information required to review these very complicated buildings. And structural engineers are gaining in their competence in these design processes. They're using very advanced tools, and it's good to have as many eyes as reasonably possible looking at these designs as you can. And so the peer reviewers are there partly because they have some experience in some particular aspect or other. And they're not just the experts who know everything and are going to tell you what to do. It's another set of eyes to help get the job right. And in a good peer review, that's what happens, is that everybody learns and the process goes along to improve the design as it's finally done. And the conduct of a typical peer review is quite simple. The engineer of record proposes a criteria and designs the building to satisfy it. That's the engineer of record's job. And the peer review panel reviews the engineer of record submittals. And one of the submittals is the basis of design document. But then the design starts, and the peer review panel reviews what's submitted for consistency with the performance objectives that are stated, it is hoped, in the design basis documents, the criteria that are there, and consistency with standards of practice. A good review provides input that promotes resolution of comments in a collegial manner, not an antagonistic one. And this is not the place for you to force your way of doing things on the structural engineer. This is the structural engineer's job. And my perspective on the peer review is that you're there to help. You can suggest things that you think might be improvements in the practice, given the particular conditions. But if your opinion is something different from what's the standard practice, it's okay to suggest it and then back off. It's not the place to impose your particular way of doing things or your particular model or your friend's materials. Now, there are some limitations to any peer review. The burden to demonstrate conformance of the structural design resides with the engineer of record, period. The responsibility for the structural design, once it's done, remains solely with the engineer of record, period. And the responsibility for the plan review resides with the building official, period. The peer reviewer has no responsibility other than to help. Okay? Not quite true, but no, the peer reviewer has a lot of responsibilities to help in the process. But it's really important to recognize that the design is the engineer of records. And the plan review generally resides with the building official. Sometimes one or more of the peer reviewers or their companies might be hired to do some of the plan review, but that's generally done separately from the peer review itself. Now, the membership of the peer review panel is established in various ways, and I'd like to suggest how it commonly happens, and it's not always this way. Turns out that the project sponsor and the engineer of record usually have some skin in the game, right? They got money on the table. They've got some brains behind the design. They kind of know what they're doing, what they're aiming for. It only makes sense that the building official and the project sponsor and the engineer of record talk about this in some way. And however it happens, in my experience, there's usually some kind of communication that goes on, at least informally, to help figure out what's the right way, who might be some people to do this peer review work. But in the end, the selection and the reporting of the peer review panel is done by the building official. And you might get unlucky and you might get lucky with who your members are. I have yet to see these panelists on any of the jobs, but they might be fun to have. Now, so the selection and the reporting is between the building official and the peer review panel. The peer review panel generally is going to have 3 people. That's what I've always seen. Sometimes there's 4. There's almost always a structural engineer of record, and this is an individual who has that license and has tall buildings expertise. There's generally some geotechnical engineer or seismic hazard expert. I mean, you heard from others around the room today that the seismic hazard and modeling the foundation, soil structure interaction is important, and it takes special expertise to do it well. And there's usually an academic, not always, but there's usually some academic involved because there may be some specialized aspect of the building. It may have some materials that are very specialized, or maybe it's a routine building, but you want somebody who's really got the fine touch of what works and doesn't work in concrete or steel or what have you. And so it's good to have that very specialized expertise there. So that's a typical makeup for a panel. And usually these panelists are selected as individuals, not as companies. I mean, it can be done where you select the companies as companies. But usually, as I've seen it, the selection is on the basis of the individual expertise. And Farzad likes to make the point that when he left JAMA recently, he was the peer reviewer on several jobs, and he took them with him. Okay, they came with him because he was the guy who was doing the review, not Johnny Martin. There especially needs to be recognized that there can't be any conflicts. It's got to be clean. There cannot be connections between the reviewers and some other parties involved here. And there can't be any quid pro quos. You know, for example, if John over here is reviewing one of Ron Hamburger's jobs, you can't take him out for a drink the night before and say, hey, you know, if I help you with your job, maybe when it's my turn, you'll come help me. Doesn't happen, does it?
Never, ever.
Never, ever. So, I mean, it's got to be clear. There cannot be any of that going on. In many cities, what's done is to kind of mix up the reviews such that when there's a design going on in one city, they bring outsiders in to do the review. There's a care taken to avoid that perception even of that going on. The contracting models vary from city to city. Sometimes the money goes from the project sponsor to the building official, building department, excuse me. I was waiting for that correction. And from there, it can go directly to the peer review panelists. That is a clean way to handle things because the reporting is going back and forth that way. It makes some sense that the money goes that way. It's not unusual for, though, the contract to go the other way, the contract going directly from the project sponsor. That's the person who has the cash, and up to the peer review panel that way. And it does provide a possibility for a conflict of interest to occur. I haven't seen it, although I'll maybe show one example where it's been reported such a thing almost happened. As for the operational aspects of a typical peer review panel, Steve, I tried to find a picture of you for today, but we'll have to do with this guy. But building officials usually are handsome fellows. And the first kickoff meeting is usually a meeting that takes place in a big room around a big table. And the building official comes with usually a few people, seldom just one person. The project sponsor is dressed like that and brings people with him or her. The engineer of record, there's a team shows up, and then the peer review panel shows up. And one of the first things that needs to happen is to find who are the people who are going to run this thing and keep it organized. And so there's generally, one of the first things established is what are the points of contact within this process. And of course, in the building department, there's got to be somebody. On the peer review panel, there has to be somebody who's going to be in charge, the point of contact so that information flows properly. And then on the engineer's team, there's nothing worse than having 3 different names for the building project. You know, one is the address, the other is the title of the building, and the other is the developer. And nothing worse than having 3 or 4 different people from the engineer of records office sending you stuff at different times. You've got to establish who are the people, and that's the only set of people from whom information flows. And generally what's expected is that the building official is in the room, either literally or figuratively on the phone, in every official meeting that takes place, so that the building official knows what's going on. There's not little secret meetings and arrangements going on outside of that. It's good to be that way. The project sponsor's there in the first meeting telling you about the importance of the job and how essential it is to get it done on time, and then they kind of disappear. And oftentimes you won't see the project sponsor anymore. Sometimes a particular sponsor will show up again and again, or they'll have somebody come, but usually they don't have the interest to keep coming to the meetings. Sometimes they do. The distribution of the work. As I usually see it, the structural engineer of record is the person who manages the peer review generally. And it's really important because they've got the license, they're structural engineers by interest, they have a team to back them up within their office. The academic doesn't have the team, and things can sort of fall on the side if you count on the academic to run the show. And so it's, at least that's the excuse I always use to get me out of the job. But that's the single point of contact. Their team provides support in terms of managing documents that have to go back and forth. There has to be review of the computer models, and I'm not going to do that in detail. I'm not going to open up Perform and look inside. There's somebody in that office who knows how to do that, and they report back to the peer review panel. This is what I see there, or I can't get this thing to work, it's not running properly. Go back to the engineer of record and figure out why. And then that office also prepares letters for approval by the peer review panel and then for submittal. The geo or seismic hazard expert has that particular expertise and is providing that support mainly. Sometimes they're involved from the beginning to the end, and sometimes they're only involved actively while that part of the work is going on, and then there's the academic. The scope of services. I struggle with this every time I work on a job because the company always wants me to have insurance for my car, for my practice. They want me to have licenses in the different states, and I always have to argue through this whole thing. But anyway, we work through a scope, and the technical side of this is, what are you going to do? You're going to review the design approach, the seismic hazard, the modeling approaches, the acceptance criteria, and I always add in whatever else happens that we didn't anticipate. You review early design concepts and details. You review the final design. It includes all the computer input and output to make sure what is being reported to you as results actually makes sense. You don't just say, hey, are you running a Perform model and do you feel good about it? No, you check the model itself and the input and output by running it in the SE's office. And you check the analysis results and then the details as expressed in the drawings. You also agree you'll participate in meetings, and if things go well, there's never a promise, but if things go well, you will sign off on a letter that says, yes, this meets the equivalency requirements of the code. And then you recommend to the building official, you can approve it if you so feel fit. Anyway, the timeline and deliverables. The peer review panel is there to facilitate the project, as I mentioned, not to impede it. The review should start early. It's quite important for that. There is this kickoff meeting. There's a basis of design stage when you come to an agreement with the engineer of record on how they're going to design the building. I'll show an example of what the table of contents might look like. There's the geo report, and the seismic hazard has to get reviewed and agreed to. That's usually a next step. There's oftentimes a request for an approval for the excavation. How deep do you want to go with the foundation? So to know how deep to go with the foundation, you need to kind of know what the foundation mat's going to be, which means you've got to have a pretty good idea of the entire building design by that stage. And then there's a partial or complete structural review and the final approval letter. And each of these circles indicates that there's a back and forth going on in this process. It's not a, here's my basis of design, send it back to us with your signature in a week. There's almost always once back and forth, and so each of these processes can take a month or so to get through. It's not immediate. Now, the peer reviewers should be on the watch for unrealistic schedules. They happen occasionally, not too often, but sometimes they do happen. Here's an example where it's suggested that in step 3, there'll be a submittal of response vector to the peer review panel sometime between September 26th and October 7th, and the approval shall occur sometime between September 29th and October 8th. And you know what that means? That means one day. That's not going to happen. If you look further down, there is the expectation that the team is working for 8 months on their design for the MCE, and the panel is going to be able to review all that in 1 month and put a stamp on it. When you get something like this, the best thing is to raise your hand right away and say, this is unreasonable, let's get this straightened out. Because if you don't notice this right away and get this corrected at the beginning, it'll come back to haunt you later on when everybody's complaining about the fact that you're holding up this unrealistic schedule. The design documentation, there should be a basis of design document that's developed right at the beginning. And this basis of design should describe what it is you're going to design, how are you going to analyze it, what are the criteria that you're going to use to decide if it meets or doesn't meet its performance objectives. All that should be spelled out. Everybody should agree to those things before you get down the path of the design. If you're into the design and you haven't agreed on all those things, everything is an argument all the way. It's, get it done at the beginning, and then it's routine to demonstrate conformance with the requirements. Other documentation generally required is the computer models. They get sent to the panel, and the panel looks at them. By the way, it says here, we're here to help you. So in other words, if you can have a meeting in which you walk us through what the model looks like, and then tell us how things are organized, and then give it to us in an organized way rather than giving us a pile and say, here, you go figure it out. It'll go much faster if guidance is provided. Anyway, documentation on how things are designed and so forth is required to get through these various steps. The performance verification has to be provided in writing. Typically it's a PDF these days. And in the last 5 years, even I've learned how to review a PDF diagram. I used to have to print everything out, but I'm learning. But all the performance checks are checked, and the drawings are looked over page by page. Everything is scrutinized to be sure that it passes. Now, a typical basis of design table of contents might look something like this. And so maybe you can read it from where you sit, and I can see it from here. But there's an intro. We're putting this building together, and it's so many stories, and this is what it's going to be used for. There's maybe a general section that says, this is the exceptions to the code that we're going to take. This is what we think the risk category is. These are the materials we plan to use, sort of general stuff. The design process, this is how we're going to design walls. This is how we're going to deal with flexure and shear. All the details should be laid out in some fashion that everybody can agree to in a lot of detail. It doesn't have to be organized like this. This is company specific, and the peer review panels that I know of are accepting of many different styles. But what we're not accepting of is a basis, a design document that says trust us. That would never make sense, okay? And the kinds of things that might be inside the basis of design document or appended to it. So, oh, by the way, this is how we're going to set up the performed modeling. It'll look like this. This gives the panel confidence that the team knows what they're doing. Another example of how this might be laid out. If you've got some experience in designing buildings like this in the past, maybe you show an example of how you might demonstrate, as is an illustration, how you might demonstrate performance. These are the kinds of things we'll give you as we go through. And ultimately, these are the kinds of things that you're looking for. What a marvelous design. Look at this design on the right. The DCR1, everything is piled right up against the edge. Perfect design. All right. And then in the process, once it gets going, everything, there's a lot of stuff to keep track of. Sometimes these reviews last many months. I've seen them as short as 7, 8 months or so, and I've seen them as long as 2 years. And you can forget what's going on in this process. So it's very important to have a log that documents things. And usually the structural engineer of record keeps this. It has numbers of comments, references particular documents and pages. This is the comment. And the comment and the response are better if they're friendly and they're helpful. You know, it's nice to say the consultant should clarify which set of values were used in the analysis rather than, what the hell were you thinking not giving us this thing? And the response should be, this has been corrected, rather than something like, it should be intuitively obvious to the most casual observer that the answer is this. This is not an antagonistic process. It should be a collegial and helpful one. And the peer review panel in the end marks it resolved or not, and when it's resolved, you don't go back to it. There sometimes are disputes. I seldom have seen them, but they can arise. I've heard of some. And they may relate to the level of complexity, the interpretation of the results. The building official is the final arbiter in these things, and sometimes if it escalates to an advisory panel, it could happen. I've never seen it. But I have had structural engineers of record refer to me and the other structural review panel members as being incompetent and not irresponsible in terms of the fiduciary matters of the project and so forth, and that's going to go nowhere. and it didn't for a long time. All right, so how much time do I have, Jay? 15. Wow. I think I lost some time at the beginning, but okay, we can do it. So here's just some examples of things that you run into along the way. And don't worry, 15's fine. We often hear, the peer review process, it takes too long, it's too expensive, and it's too uncertain. And project sponsors sometimes try to steer away from this process because of that. And sometimes that works, and sometimes it doesn't work. And so here's some examples that we've come across over the years. This is one Farzad put in here, the dual system that was not. And this is the story where the developer came in with a Southern California firm for a Southern California building, and it was a dual system, and the developer didn't want the dual system, just wanted the core wall, and so they went back to an East Coast company, as I hear the story told. And the special moment frame ended up inside the core, with no frame outside the core, but it was just columns inside the core, and they tried to pass that as a dual system. And is the city going to say, yeah, sure, that meets the requirements of a dual system or not? And I think in this particular case, they said no. And so the developer, the project sponsor, got a peer review panel on this, and the peer review panel said, no, that's not a dual system, that's a core wall. And so away that went. This is the story of the dual system that became one. Now this wording is a little off here, I think. This is the case where a developer decided that the peer review process was too difficult. Let's build a dual system to avoid the process of peer review. And so a legitimate dual system was developed, 50, 60 stories tall. The city was a little leery about the building because it was rather tall, so they brought a peer review panel in anyway. So the project sponsor got the worst of two worlds. You know, they got a dual system and they got a peer review. And the engineer of record sort of kept something secret from the panel, which was that they intended to substitute a different product for some of the reinforcement. I'm not going to name anything. And after the project was approved, the building department was inspecting the site and noticed that the reinforcement didn't look like the reinforcement on the plans, and so called the peer review panel back in. And it turns out that the substituted material had never been tested in a laboratory with anything like 10,000 psi concrete, and the peer review panel said, you're going to have to run tests on this. And so by this time they were up to story 5, and there was an emergency design of a test series that went in some mysterious laboratory somewhere. And by then they're up to level 9. And the tests were set up in the laboratory to see whether this new material would work. It's reported that the project sponsors had the taxi cab motors idling by the back door while the tests were running in case they needed to make a quick getaway. And fortunately the test passed, barely, and the taxis went away and there was a big party in it, and the building stands, but it came really close to being a big disaster. So don't try to sneak something through. The armed struggle over stress limits. Oh, this was another example Farzad had run into, where in the basis of design, absent was the limits on the shear stresses in the walls. And so the designers came and showed the designs, and instead of 10 or 8 roots F prime C shear stress limits on the walls, they were 12s and 14s and 16s in several places. And the peer review panel said, well, you can't have stresses that high. Only 10 is the maximum in any peer, or 8 on average. You've got to redesign this. Well, months passed, they came back again with the same numbers, in hopes that the pressure of getting the job signed off would just make this go away. Well, it didn't. And so the review process did indeed become too long, because they had to redesign the whole system and get it to be properly within the limits. So sometimes peer review isn't pleasant if you're trying to get around something. One of my favorites, the SPRP's suspended animation. So this was a job in which the project sponsor came in and it's an emergency. We've got to get this job done quickly, expedited, as all these jobs are. I've never seen one that wasn't that way. And the engineer of record spent the first couple months working on the basis of design and got it approved, and then disappeared. And 8 or 9 months later, the phone rings. It's time for a meeting. And the engineer of record shows up. The design's done. All of it's done. And we need the approval no later than 1 month from today. And what do you think we peer reviewers? You think that we're just living here in suspended animation for 8 months waiting for something to happen? There's other jobs going on. And so these guys had to get in line behind all the other jobs that had come along, and it was a long time before this one actually got finished. So no, the peer review panel is not in a state of suspended animation while you do your work. You've got to keep the panel involved all the way along. Example 5, conditioning payment on approval. You know what this is about.
Damn it.
The panel was having a tough job, and it was costing more than was anticipated legitimately. And so the panel chair went back to the developer and said, we're going to need some additional funding to get this job done. And the developer sent their attorneys in, and the attorney said, yes, we will pay you if you agree to approve the job in 30 days. What? Oops. And how can we approve something we haven't seen? How can we promise to approve it? And so this requires some working out. It should go the other way. You don't get the letter unless you pay, right? Anyway, things have always worked out for me, except when the economy went belly up in 2007 and 8. We all lost a little money then. Example 7, conditional mean spectra. We talked a little bit about conditional mean spectra and scenario spectra today. These have had a life where they were first introduced and then where they've become more routine. And the first example, 7A, was when a project in California came up. First time I ever saw conditional mean spectra. The geotech was pushing the conditional mean or scenario spectra on the job. And the engineer of record said, hey, this is the latest thing, let's go ahead and do this, and started down the path of using spectra that had been conditioned on a first mode period. And then, of course, the peer review panel came in and said, well, what about period 2 and 3? This is the story John Hooper presented a little earlier. What about the other modes that are also getting excited and that happen to be now falling like around here? And the scenario spectrum you're using is about half of what the target should be. You're going to have to get 7 new motions, and you're going to have to run 7 new nonlinear response history analyses, and you're going to have to take the answer as the envelope of those 2. Whoa, wait a minute. So back out, and had to redo the whole process and restart the thing over again with uniform hazard spectra. Things have evolved. Engineers of record are more aware of what this entails. And you heard Mr. Hooper reporting on the big project. What's the new name of the project in?
Salesforce.com.
Salesforce.com in San Francisco. I'll never be able to get used to that name. Anyway.
We will eventually, Jack.
Transbay Tower. They volunteered to do 11 motions with spectra conditioned on 2 different periods, and it's the technology's come along now to where that can happen. Example 8, A, B, and C. What do you mean the effective damping is 2.5%? Damping's 5%. It's always been 5%. Well, we've gotten past that. That is not a problem anymore. 8B, Rayleigh damping scale to periods T1 through T3. Well, it's commonly accepted that if you're going to use Rayleigh damping in software, then you would want to condition your input variables such that you get 2.5% damping at something like 1.5 times T1, so when your period softens a little bit. And then somewhere around T3, you'd also want to be at about 2.5% damping. Well, you'd be surprised how many engineers think T1 is the first mode translational period east-west, T2 is the second, is north-south, and T3 is the first torsional mode. You'd be surprised how many people set up their coefficients that way. No. That's the third translational mode, okay? All right, in each direction. So, but we see it, we still see it. Now we're starting to see some analyses being done using modal damping, which is possible in Perform. Seems to be working fine. Read the manual. You always want to have a little bit of Rayleigh damping in there because as your periods elongate, you don't want them skipping off the damping. And if you put a little bit of Rayleigh damping in there, you can get these to work pretty well. So modal damping, you can set it up to hit all your modes and not play around with this. Example 9. I keep hearing that bell in the back and thinking my time is up, but it's just the elevator.
Maybe it is.
Example 9. The engineer of record says, strain capacity of unconfined concrete is 0.003. It's in the code. And I've done my analysis, and my strain in the wall is 0.00297. Therefore, it's less than the Spaulding strain. I don't need to provide confinement. And then you ask, well, do you know how accurate your results are? And the young engineer says, my results are very precise. No, wait a minute, I didn't ask you how precise they were. And that's when the reality check is required. You either cut the strain limits to be something you're confident is going to be acceptable? Like, I would cut this in half. Or demonstrate that you actually know how to perform against some test data, and you can predict, you can calculate when you're going to have spalling occurring. And most engineers will opt to back off on their precision here and put confinement when they get to something like half what they think the spalling strain is. These computer softwares aren't that accurate. Very precise, but not so accurate. Now we're at 5 minutes. Okay. My favorite. Example 10. This is fondly known as the loop-de-loop hoop. And the loop-de-loop hoop is something you have to look at carefully. You won't believe this. It starts here, goes around here, down, loop, loop, down, around. One piece of steel, mind you. Loop. I'm having a hard time with this mouse. Loop. You can imagine this when they're bending this, and the guys have to stand like 60 feet away because this piece of steel is. Anyway, it goes around and around and makes a hoop. And you can imagine that if you left out the corner bars on one side and you overlap two of these and dropped a longitudinal down, charge that bar down through there, and you do this multiple times, you have a daisy chain of loop-de-loop hoops. And the question is, what is this good for? I think it's probably it's okay for supporting longitudinal bars against buckling. It's probably okay for confinement. Is it okay for in-plane shear? Every place I look, I see steel. It looks like there's something there. But this loop, this thing that bends around a bar, is that really providing a continuous tie along the length? I don't think so. And so, what's that worth? Is it worth half of a tie? Is it worth all of a tie? Is it worth zero of a tie? And this is where you start the negotiation, and maybe this needs to be tested before you even consider this. Anyway, this is like the Argentine ant. It came from some unknown country, probably. It deposited itself on some ship in Southern California and worked its way up, I'm sure, to San Francisco by now. If you haven't heard about the Argentine ant, I hope it never makes it up here, but this is on its way. So you'll have to think, Steve, what you're going to do with this when it shows up. It's a marvelous device. Example 11, the diagonally reinforced coupling beam. Everybody knows that all of the shear is carried by the diagonals, right?
Absolutely.
Absolutely. Therefore, who needs the concrete? And so we've started seeing designs in which the coupling beam is the go-to place for all the heating ducts and everything else. And in jobs I've been working on, we've been telling the building official, tell them no. Tell them that the city only allows 4 inches little pipes going in. And we don't know whether taking that chunk of concrete out makes a difference or not. Now, if a sponsor wants to test that thing and shows that it works, I'm all for it. But until that's done, we don't know that you can take that big chunk of concrete out. But we see that on lots of jobs. And if you find this out at the end of the job, it's bad news for the project. Lots of stuff has to change. Construction details, example 12. Wall slab interfaces. Well, on the left, it's probably a code violation. B, you could puddle the concrete. It's a mess, but it can be done. You can hold back the slab concrete and then cast the wall through in 2 lifts. Or you can slip form the wall and then have a cold joint in a mechanical connector. It's a good idea early on in the job to work out with the peer review panel and the building department which ones of these they would accept. And you often don't know early in the project what one is going to be used on the job because it's kind of a contractor's option. Got to be worked out. Foundation mats. Everybody knows how we teach, me too, how we teach the design of footings. How do you pick the depth of a footing? You make it deep enough so that you don't need any shear reinforcement. And of course, what we find when we run tests on deep beams without shear reinforcement is that the unit shear strength decreases as the depth increases. And so the question arises, should you be allowed to design deep foundation mats without any shear reinforcement? Because this is what the evidence, the only evidence we have shows. And so the way I usually approach this on a job is I point out that this kind of data exists. I point out that this is not a code-conforming building. This is a core wall-only building, and therefore you're outside of the code design. So you can't fall back on the fact that this isn't required in the code. If you want to do this because it's allowed by the code, put a dual frame with it too. So what do you want to do? And usually we can get some shear reinforcement in there. And once you put a little bit in, like a number, what is it, a 9 or 11 bar every meter or so, it takes care of it. Wall irregularities. I'm getting close to my end here. But you see things like this all the time, a shear wall that the openings come down and then they stop. And lots of questions on things like this. What's the force transfer right there? You hear those kinds of questions, or here's a little opening down here. And how does the shear force that's in this uniform wall, this continuous wall segment, how does it transfer from that to being non-uniform when there's an opening? What do you do? And so that's another question that comes up on all sorts of jobs. How do you get the shear that's uniform up at the top dragged over to be something that's on two sides? It must require some kind of a drag bar of some sort. All right? And Jay, I think my time is up. And I had one more slide, but I'm not going to show it.
Go ahead. Now you've already...
There it is. It's my list of, I made it up last night, but it's my list of the things that I typically will go through and look for on a job. And we don't have time to talk about all the things, but when I look at a job, what are we looking at? You look specifically at certain things, and then we always find something else while we're looking anyway. But this is a list that I think is always worth keeping in mind. And you can't write it all down, but you all have cell phones, I know, and you can take pictures. So thanks very much.
We can leave it up for the frame. So thanks, Jack.